Howdy folks, welcome back to another CS 120 honors lecture. In today's video we're going to be talking more about threads, thread ordering, so how threads run parallel to each other, and how to share data between threads and how ownership plays into that. So today's lecture will hopefully be covering sort of how we can run multi-threaded code, how it appears to be run on our processors, and just sort of how we enforce some type of ordering in our code. This is sort of going to lead up to the next lecture where we talk about how you can actually enforce a partial ordering on how code gets run between threads. Then we're going to sort of do some more review on MPSC, some more review on how you drop the senders, and then more on thread execution order towards the end. So hopefully this gives you a good understanding of how MP3 works. Okay. So I have this bit of code here. Essentially, it spawns 5 threads. Each thread is going to print hello from the thread number 3 times and sleep for 1,000 milliseconds in between. And then this main thread is going to effectively wait for those threads to finish and then join on them and then print out how long this the main thread was waiting for this join call. So we talked about blocking functions in previous lectures. Join is a blocking function. So this code will measure how long this thread of execution is blocked by the join. So any hypotheses as to how this will run? So there's no sort of guarantee of thread execution order. So there's a couple ways that this could actually run. So we have the main thread. The main thread is going to go ahead and create a bunch of different threads, threads 0 through 4. And we've said in the past that the cost of spawning a thread is negligible in the grand scheme of things, but it can be significant if you do have a shorter living program. So our code only lasts for around 3 seconds, so we're going to represent the cost of spawning a thread as some small amount of time. So once the main thread has spawned all 5 of our threads, it's going to begin waiting on thread 0 to join. So at this time instant, once we've finished starting thread 4, the main thread is going to get blocked. Then our threads go ahead and run. We'll wait 1,000 milliseconds here. Maybe due to our computer's scheduling, thread 2 starts first. And then thread 0 doesn't get to run until a little bit after 1,000 milliseconds, same with the rest of the threads. Thread 2 continues to sort of lead the pack and is going to finish first, and the rest of the threads sort of follow suit. And then again, we have thread 0 that finishes. So once we see that thread 0 is finished, this waiting on thread 0 to join is going to be complete. So the instant that thread 0 finishes, we're able to sort of print out, hey, we know that thread 0 is finished. This is how long it took. So we can expect that it took around 1 second here, another second here, another second here. Maybe that we did some work in this thread when it was running. Maybe we didn't. But we can then print out exactly how long it took for the join to happen. And then once thread 0 joins, we'll start waiting on thread 1 to join. So this little time instant is how long it will take for thread 1 to join because we're blocking on the join handle from thread 1. So blocking on thread 1, we already know that thread 2 has finished, so we don't need to join on that. We don't need to block. The join returns immediately. Then thread 3 finishes. We didn't need a block for thread 2, but we do need a block for thread 3. So we finally get there. We wait for thread 4. Thread 4 finally finishes, and we finish main. We exit our little for loop where we're waiting for threads to join and print that out. So there's no guarantee of execution order, so I want to sort of hone in on that point, and we'll see that when we run this code. Okay, so we have this code, fire off a bunch of threads, print hello for the first time, wait, then print hello 3 more times. And then here we're sort of measuring exactly how long we're waiting for join. We get the exact time before we call join. We wait for join to finish. Then we get the duration. So the current time minus the starting time, and we print that out. So go ahead and run this. We get hello, wait another second, and finally at the end, there we go. So we can see here that we're waiting for 3 seconds, slightly more, for thread 1 to join. And then thread 1, maybe it's finished early, so the cost of calling this function is very minimal, 6 microseconds. But thread 2 hasn't joined yet. We're still waiting for it. We're still waiting, what is it, like 1 millisecond? So there is a cost, there is some time that we spend blocking on thread 2. And then by the time thread 2 finishes, we know that thread 3 and 4 have already finished because the cost of joining them here is very, very minimal. So I want to run this again and show you that this isn't deterministic. This produces different results every time we run it. So there we're waiting for thread 2 again. Let's see if we go another time. This time we're waiting on thread 1. Thread 1 has some more time to finish. Threads 2, 3, and 4 are done by the time thread 1 is done. So you really can't expect anything out of thread execution order. You have to use what's known as these atomic primitives to help guarantee that order for you, which is what we'll do in the next lecture. Okay, so as you see here, we saw a similar output. We're waiting for 3 seconds for thread 0, and then we have no guarantee as to the order in which all of the threads finish. We might be waiting for thread 1, we might be waiting for thread 2 to finish. All of the threads could be finished by the time thread 0 finishes, in which case you'd see a smaller number here. So there's no guarantee as to the order they finish. Okay. Now onto a quick review of MPSC. So we said in the last lecture, MPSC stands for multiple producer, single consumer. So you have multiple threads that are producing values with these senders, and they send them to the single consumer thread that owns the receiver. Senders are clonable, so when we create a channel, we get one sender right out of the bat, and we can clone this sender and give the clone senders to a bunch of other threads, which will use the sender to produce values and send it to the one receiver consumer thread. And then we clone the transmitter and use this move keyword to move ownership of the cloned transmitter to a thread, send messages within your threads, and finally you receive messages on the main thread or potentially another worker thread using your RX. And then we said RX is this blocking call. It works similar to join in that it blocks until something happens, but in the case of RX, it's blocking until either you receive a message or all messages have been received. Okay. And then we talked about how we solve problems with parallelism. So you have this main thread that potentially has a large piece of data, and we want to split that piece of data up into smaller sized chunks. So we're going to split this original data into an owned value. So we're going to duplicate the data, not create a reference, then give ownership of this duplicated subsection of data to a thread. The threads are going to perform some computation, get a result, and then they'll send the result back to the main thread with the sender. And then we're going to use some logic in the main thread to combine the results and yield our final result. Okay. So this is the general sort of paradigm you'll be using when you tackle MP3 MapReduce. This is a shortened version of that. So what we're doing here is we're firing off a bunch of threads. We're creating an owned sub vector. This .2vec makes a deep copy and creates a separate value outside of data. Then we're going to move the owned sub vector into the thread. We're also going to move the cloned transmitter into the thread. We're going to compute some value. In this case, we're computing the sum, and then send that back to the main thread. And then in the last lecture, we said it's very important to drop the original transmitter so that all transmitters are dropped by the time we're, done sending values, so that this rx.receive doesn't block forever. If any of this is still confusing, I highly recommend going over the last lecture again, because that is where I go more in depth as to how these function calls work. So Okay. So rx.receive returns an error when all transmitters have been dropped and all messages have been received. That's what we said. We prevent blocking by dropping all transmitters, either with the drop function or by letting the transmitters go out of scope. So transmitters are dropped when they go out of scope, or you call it drop. And Rust automatically calls drop for you when a variable goes out of scope. Okay. So this is super, super important for MP3. You can use implicit drops. So in this case, we have a function that splits the workup and creates some threads to do the split up work for us. So in this case, it's the exact same code, except there's no while loop at the end that collects the results. This function simply creates the threads. Okay? And at the end, we're returning Rx. So we're passing ownership of Rx to somewhere else, and we're dropping this original TX. So the clones get dropped at the end of the thread. This original TX gets dropped at the end of the function. And then, so Rust will automatically call drop TX for us. And then we have a separate function that takes ownership of Rx and does this blocking while let receive for us. So receive will block until all messages are received, and we have finished creating all the threads and the original TX gets dropped, and all the other threads have finished and they've dropped their TX clone. So putting that all together, we can call this function split work and create threads, and then call this function receive, and receive will block for us. So because we're calling a blocking function in receive, receive blocks the main thread. That's the super important part for MP3. You'll be implementing two different functions, one function to create threads and split up work, another function to do this blocking receive for you. And then in our code, in our tester code, we'll actually run these functions, and your receive will be the one that blocks until all the work is done. So there's a blocking call and receive, so receive will block the main thread, and then once receive is done blocking, once you have all of the values, you can print that out. Okay, so we've talked a lot about making copies of the original data when you send it off to threads, and so this section will be sort of why we want to do that, why we want to make copies rather than using immutable references. So we've established that a thread owns all the variables that are moved into it from the parent thread. We use this move keyword to either copy primitive types or move over structs like strings, like senders, anything that can't be copied. So we also know from ownership rules that variables and values, they get dropped when they go out of scope. And so any data that gets owned by threads gets dropped when the thread finishes. So the big takeaway from this is we want threads to own their own data to guarantee some memory safety. So there are ways around this. There's this notion of a scoped thread, a thread whose join handle, when it gets dropped, you get a call to join in there. So, whenever you sort of reach the end of your scope, your thread will continue to block that function until the thread finishes. This is out of the scope of the class. We will not make you use scoped threads, but if you want to, they are available for your final project. But today's lecture is sort of why we want threads to own their own data to guarantee memory safety. Okay, so this is a buggy model we'll sort of be debugging right now. So let's just suppose we had a main thread, maybe we had a function call in there, and that function call created some shared data. And then that function call is going to create our threads and give these immutable references to the data, to our threads, and then the threads will sort of perform some computation on that and yield a result at the end. So let's say this is just a giant vector, and we're giving a small slice of that vector to thread 1, a different not overlapping slice to thread 2, and another different non-overlapping slice to thread 3. So let's suppose this is how our model looks like. So see if you can spot the issue with this model in these thread execution order sequences. So one potential execution order that we saw was that all threads run together and finish together. Another one is the main thread runs for a little bit, then thread 1 runs for a little bit and finishes, only thread 2 runs for a little bit and finishes. This is another potential execution order. Suppose you only had one CPU in your computer, one processing core. Well, then you can only run one thing at a time. So you'd run the main thread first, then thread 1, then thread 2. And then this is something we saw in the previous example when we're waiting for threads to join. There's no guarantee as to how long threads wait while they're sleeping. This one's another possible execution order. Same thing. So, big takeaway from this is there's no guarantee of thread execution order, which means there's no guarantee as to how long our reference lives. So, let's say we create some data in the main thread, and then the original copy gets dropped at the end of its scope. Let's say we create the data in some function call. The data gets dropped at the end of that function. Okay, but the issue is we passed a reference to that data to thread 1 and thread 2. So when the data goes out of scope, we can say that the original data goes out of scope, which means that we have an invalid reference here. We have a reference to some data that's been dropped already. That violates our Rust memory safety rules. In the other example, we drop some data at the end of this main thread. Maybe it's within a function. We drop that data at the end of the function. We're trying to run thread 1 and thread 2 with invalid references onto some data that's been dropped. That violates all of Rust's memory safety rules. So at this point, when the data is dropped, our references become invalid. This shared data could be garbage. It could be overwritten by something else. It could be, given back to another process. You don't know what's happening. So the reference we have is invalid, and so our program no longer has 100% correct certainty that we'll be producing the right result. So if you remember way back to the borrowing lectures, we said Rust references must always be valid. So the borrowing rules enforce the fact that the data is alive as long as the reference exists. So the big takeaway from this is to get around that. We create a copy of the original data and give that copy to the thread. And use this move keyword to move ownership of this copy into the thread. So in MP3, you're going to be creating a sort of subslice from a large data set. And so the big takeaway is clone that subslice, clone that data. It is clonable. You should create a separate copy. There are techniques to consume this. So consume the first data set and split it out into 3 subsections. There's a clever way to do that in the MP, although we do allow you to use clone. The more efficient way would be to consume this data set and produce a bunch of other smaller data sets. Okay. So if we were to use this model where we clone the data set, we give each thread an owned copy, then our execution order is fine. The original data set, it gets dropped at the end of the main thread, but thread 1 and 2 own their own copies of the data, so they're able to continue. We're not using any invalid data because thread 1 retains ownership of whatever data it was given. Same thing in this example, the original data gets dropped at the end of main, but thread 1 and 2 are able to continue because they own their own copies of the data. So nothing bad happens. We do not violate Rust's memory rules. The copy that thread 1 owns goes out of scope here. The copy that thread 2 owns goes out of scope at the end of thread 2. All is fine. So we obey Rust's borrowing rules. Nothing bad happens because we're not borrowing. Okay. So hopefully this slide will give you a bunch of hints on your MP. So split up your data into own chunks. We have a function that makes you do this. We give you a vector of some strings, and we want you to produce a vector of strings. So each inner vector should be roughly equal size, and it should be all the elements from the original vector split out into 10 different equal size chunks. I believe the number of chunks we ask you to split out to is variable, so we'll leave that to you to implement, but For example, if we had 1,000 elements in this original vector, we want you to produce a vector with 10 inner vectors, each with 100 elements. Okay, so in MP3, you take a vector of strings, you're going to clone each string, and then place the clone into one of your inner vectors, which forms a chunk. Okay, and then we're going to ask you to create threads with that. So use an iterator that takes ownership and consumes your data. So you'll use this into_iter function to take ownership of this outer vector. This outer vector is generated from your split into chunks function. And then you'll spawn a thread for each chunk, give each thread a separate chunk, do that computation within the thread, and finally use the sender and receiver pair to send this computation result back to the main thread. So this is sort of 2 lines of code that you should have in your function that spawns threads. You call split into chunks, and then you iterate over chunks and call thread spawn. So hopefully this gives you a good start on MP3. I'll keep this lecture short. It's meant to be sort of catch up and review and hints on how to proceed. Hope it helps. Take care.